So I gave the homework, basically the homework of this week, and that's going to be due after the Thanksgiving break on Friday. So that's going to be some time. Yeah, so you can look at the schedule, and then it's going to be December 4th. Okay. So I think it's already 10. We should get started. This class, we're going to go through quite many topics. So one is about the calculation for the adsorber, and then we're going to also spend some time talking about the project. Okay. So if we again do a recap of our last class, we mainly talk about the adsorption process, right? So we introduced some term called the isotherms. So the isotherms just represents what is the capacity of the activated carbon or adsorbents. So what is a capacity versus the partial pressure of the VOC? Right, so we derive some equations to calculate this capacity term here. So finally, I mean, by equating the rate of the adsorption, let's say rate of adsorption equal to the rate of desorption. So we found that the area that's covered, I mean, the area of the adsorbents that's covered by the VOC is indeed dependent on the partial pressure. That's K1 P bar plus 1, right? So based on the P bar here, which is the partial pressure, then we can calculate. Basically, it represents how much of the VOC this adsorbents can collect, right? So if I ask you, how does the capacity of the adsorbents change with the partial pressure of the VOC? So which option should we use? I mean, which option is correct? I'll give 10 more seconds to answer this question. Okay, we'll stop here. So the correct answer should be C. It should increase linearly and then in the beginning and then become a constant. So the reason for that is if you just look at this, this answer we got here. So the F, we mentioned that this is basically the area of the adsorbents, let's say activated carbon, covered by the VOC. So basically, the capacity, this, let's say this is A here, okay? So the capacity should be proportional to the F, right? So whatever happens to the F, which is the area, it's going to happen to the capacity. So we just need to look at this equation here, okay? So since it has the partial pressure in there. So we mentioned that if the partial pressure is much, much smaller than 1, then what this means is that this is basically, this is a very dilute system of the VOC, right? And then what this also means is that K1 P bar is much, much smaller than 1. So what this means is that the F is going to be equal to K1 P bar divided by something very close to 0 plus 1. So this is going to be K1 P bar, okay? So what this means is that at the beginning, when the partial pressure of the VOC is very low, then this capacity should increase linearly, right? That's why when we draw the capacity, in the beginning, it's just increase linearly. And then when the P bar becomes very large, let's say P bar much larger than 1. If it's much larger than 1, then you see that basically this term is going to be much larger than 1. And then this whole term is going to be almost equal to 1. Okay. So if it's equal to 1, it means that it's going to taper, right? And then get to a constant. Okay. So that's why we're going to choose C. Basically, the capacity of the adsorbent increase with the partial pressure of the VOC in the beginning and then become a constant, right? So I hope you can understand this this trend here, because we're going to use this relationship to design our adsorbent system. Okay, so just to see whether you understand this, let's do this quiz again. Okay. Five more seconds. Okay, all of you have answered. All right, so I'll end it here. Yeah, so we should choose C here. All right, so this is how we characterize the capacity of the adsorbents as a function of the partial pressure of the VOC. Okay. So then, since we already know how the isotherms look like, so how do we measure it? How do people measure it? So there are two methods mainly. So one is called the static method. So the static method just means that we're going to create a chamber and then put a scale on it, right? So basically, we're going to load some activated carbon or adsorbents here. And then at the same time, we introduce the VOC into the chamber. So to characterize the isotherms, basically at each point of the isotherm, this is under equilibrium, right? So basically the rate of the adsorption should be equal to the rate of the desorption, which means that we have to probably wait for a very long time to let the VOC to get attached onto the adsorbents, and then also let it detach so that they're in the equilibrium. So that's why the static method is going to take a very long time. So basically what we do is, let's say if we introduce 1 ppm of the VOC, and then we wait for several hours. And then after that, we measure what is the mass of these adsorbents, because now since the adsorbent already absorb these VOCs, their weight is going to be different. So we can measure a mass difference, right? So the mass difference is going to be related to the capacity. So the disadvantage for this method is that it's going to take a very long time, although it's very accurate, right? So that's why people also come up with a dynamic method. So the dynamic method is we're going to set up a column of the that's containing these adsorbents. So basically pack this column here with the activated carbon, and then we're going to introduce a VOC. But when we introduce this VOC, we introduce a pulse. So basically we introduce a very high amount and then shut off the valve. And then we introduce this flow into this packed bed of the activated carbon. And then by analyzing basically at each height, how much of the VOC are there, we can extract some information regarding the dynamic process for this adsorption. Then we can also use the data to convert it into the capacity. Okay, so the advantage for this dynamic method is that we don't need a very long time, but the result might not be accurate, right? So this is how we measure the isotherms. So since we know that the isotherms are going to look like this way, right? So it's going to increase linearly with the partial pressure, and then basically reach to a constant with a partial pressure. So how do we plot it? I mean, of course, this is a way to plot it. But if you think about the engineering application of this isotherm, basically we have partial pressure and the capacity written here. We know that basically this capacity is related to this K1 term here. So the K1 is further related to the rate right? The rate of the adsorption, the rate of the desorption. We know that the rate, basically K1, is a function of temperature. So what this means is that, let's say we just talk about the adsorption of the methane with the activated carbon, okay? So then we can establish a curve at room temperature, and then it looks like this. But in industrial applications, we may need to operate the flue gas at, let's say, 50 Celsius, right? If it's 50 Celsius, since this K1 term is different, with temperature, we may have a different curve, right? We know that the higher the temperature, the more difficult for the active carbon to absorb the VOC. So the curve is going to look like this, right? So this T2, T1. If T2 is higher than T1, then the adsorption or the capacity of the active carbon will become lower, mainly because it's going to be easier for us to release the VOC from the adsorbents, right? For different temperature, there's a curve. And we may have different curves for different temperatures. And this is just talking about the methane. So there are also ethane, right? And then butane, propane, so on and so forth. So if we just plot this curve, it's going to be very crowded. And that's why people combine all of these data and then try to look for some commonalities in the curves. And the way we plot it is by plotting it in a different way here. I mean, with a different parameter here. So if you look at this curve on the left, this figure here. So the y-axis, again, it shows the capacity of the activated carbon. So the title for that is volume adsorbed in liquid per 100 grams of the carbon, okay? So this is still the capacity of the activated carbon, but it's showing the capacity in terms of the volume of the VOC that's being absorbed, okay? And also, basically, this means the amount of the VOC, right? So, for example, if we're looking at this point, if we're looking at, let's say, this point here, okay? So what this means is that if this value is equal to 10, then it means for at 100 grams of the active carbon is going to adsorb 10 centimeter, 10 cc, or 10 centimeter cubed of the VOC in liquid, okay? Also pay attention that this is talking about the VOC as a liquid, not in the gas form. So we are also showing the parameters. I mean, the parameters on the x-axis is also different. So if you think back for this curve, we're plotting it as a function of the partial pressure, right? And for this curve here, it's still a function of the partial pressure, but we're adding more parameters. We're including temperature, we're including the molar volume of the VOC species, we're including the vapor pressure, and also the partial pressure of the VOC we're interested in, okay? So the advantage for plotting it in this way is that people found for chemicals or for the VOCs with very similar structures, let's say methane, ethane, this is CH4, right? C2H6, C3H8, C4H10, C5H12, C6H14. Okay, so for these groups of the VOCs, they're going to align on a straight line here. So all of them are going to basically collapse onto a single line. So this is going to be very easy for us to identify what is the capacity of the adsorbents when we're using when we're trying to absorb one of the VOCs or trying to deal with this air pollutant, right? So for example, if we're interested in the pentane, we don't need to look for curves that's representing different temperature, different partial pressure, different chemical composition, but we can just use this one single curve to calculate what is the capacity of the active carbon. All right. So let me just write out the parameters that's showing in the x-axis. So here, the temperature, the T is the temperature, okay? And this temperature is in the value or has the unit of Kelvin, all right? So this V prime here, this is called the molar volume. So you can just think about it as a parameter showing what is the volume per 1 mole of the VOC in liquid. Okay. Volume per mole. And that's why it's going to carry the unit of centimeter cubed per mole. Okay. And also I want to point out that this is showing the value in liquid instead of in the gas. Okay. So for example, if I want to know what is the molar volume for water, okay, we know that 1 mole of water is equal to 18 grams of water, right? And then we know that for water, its density is 1 gram per centimeter cubed, right? So 18 grams means 18 centimeter cubed, right? So that's why the molar volume for water is going to be 18 centimeter per mole. Okay, so this is how we calculate this molar volume here. And then this PV here, this is the partial pressure. And this is the vapor pressure. Okay, so the saturation vapor pressure. And this P bar here is the partial pressure. Okay, so you may wonder, I mean, this curve looks quite different compared to the curve that we just talked about, right? It seems that this curve is increasing in the beginning and then it's a constant. But actually, if you notice that this P bar, which is a partial pressure, in this equation or in this plot is in the denominator, right? So basically, the larger this value, the smaller the partial pressure, right? So that's why when this term is very large, which means that the P bar is very small, let's say the P bar is much smaller than 1, then this term is going to be infinitely large. If this term is infinitely large, then we're going to have a lower capacity, so which is basically showing the points over here, right? And then also if, let's say, the P bar is much larger, it's very large, okay? But we know that the P bar, which is partial pressure, have to be smaller than the vapor pressure. Otherwise, smaller or equal to the vapor pressure. Otherwise, it's going to be supersaturation. Under the normal condition, the partial pressure is smaller or equal to the vapor pressure, right? So what this means is that the maximum partial pressure we can get is going to be equal to the vapor pressure. And basically the capacity is going to be a constant at those locations. So if we look at this term here, since we have the log of PV divided by P bar, it means that when the partial pressure is very large, then this term is going to be 1, right? This ratio here. So the log of the ratio is going to be 0. So we're getting close to this point, right? And you can see that this line actually converge to a constant, almost a constant, when this whole term here is very small, right? Or the vapor pressure is getting very large. So based on this curve, you can also see that the temperature is affecting the adsorption, and also the molar volume will affect the capacity of the adsorbents, right? So this is just talking about the a group of organics, let's say methane, ethane, and so on. So if we're talking about some other species, for example, we're talking about hydrogen sulfide, right? Carbonyl sulfide, carbon disulfide. So for these species that contain sulfur inside, then they're also going to convert on a single line. Okay, so this is the advantage of showing the capacity in this way. And this is generally how the air pollution engineers are going to use or going to basically this plot is a preferred plot for designing the adsorption systems. Okay, So this is how we plot it. And then we're going to go through an example of how we're going to use it. But before that, let's think about the industrial application of this adsorption system. So here I'm just drawing a bed, basically a reactor or a adsorber for removing the VOC. So the way it works is we're going to introduce the polluted gas species from the top, and then this is the outlet gas flow. So the white or the blank area means unreacted or the unabsorbed active carbon, okay? So you can see that in the beginning, when the active carbon is very clean or doesn't have any VOCs, you can see most of the gas are going to get absorbed by the top layer of the active carbon. So that's why we call this saturated carbon. And since the saturated carbon cannot absorb any VOC anymore, so basically the absorption zone is going to be the layer that's further downstream of this saturation layer, right? And then further downstream, we have the clean carbon. But after some time of the operation, we're going to have a basically a thicker layer of the saturated carbon and also thicker layer of the absorption zone. Okay, so basically the thickness of these clean carbon layer is going to get reduced. And finally, if we operate it for infinitely long time, we're going to have this completely or most of the active carbon are saturated. So we're not going to collect VOC anymore. So what we can do is we can measure the concentration of the VOC at the outlet of this adsorber. So what you can find out is that in the beginning, because the active carbon is very clean, so that's why we're not going to measure any VOC from here, okay? So at the beginning, the concentration is very low for the VOC because most of them are already absorbed. But then as time goes on, we're going to see some of the VOC getting leaked out. So you see the concentration is getting increasing until we hit a point, which is called the break point. Okay, until we hit to the point of called break point where the VOC concentration is going to increase rapidly. And then when the whole bed is saturated, we're not going to control the VOC anymore. So basically the concentration of the VOC at the outlet is going to be very close to the concentration of the VOC at the inlet. Okay, so in industry, we want to basically regenerate the active carbon before it hits to the break point. Otherwise, the VOC will get leaked out, and there's no way we can control these polluted gases anymore, right? So this involves in the basically how much of the active carbon can we use in the entire bed, okay? So, so in industry or under actual plant operation conditions, so the bed capacity or the capacity of all of the active carbon will seldom exceed 30 to 40% of that indicated by the equilibrium isotherm, okay? So for example, if we're talking about this curve again, so this is the curve showing the isotherm, right? And if we're talking about this point again, so and according to the equilibrium and also according to the isotherm, right? If it's at this point, then we know that the capacity of the active carbon is 10 centimeter cubed of the VOC in liquid per 100 grams of the active carbon. But industrial application, if we found this point, then we want to make sure that the actual capacity is just 30 to 40% of this maximum capacity. So what this means is that in our design, we only want the active carbon to absorb around 3 to 4 centimeter cubed of the liquid per active carbon, per 100 grams of the active carbon. Okay, so we only allow this amount of the VOC to be absorbed, right? So this is mainly talking about how we operate it in the real active carbon absorption systems. So now we can go through an example problem. I have to say that for designing the VOC adsorber, this is going to be the central problem Okay, we have to understand how this is being solved. So I'll just briefly read through the question. So it wants us to prepare a preliminary design for a activated carbon absorption system. Okay, so to control the stream of the solvent-laden air, which is basically some VOCs in here. Okay, from certain exhaust system. So the exhaust stream temperature is 95 Fahrenheit. So it's providing us with the temperature, right? And it contains this amount of the N-pentane. So that's C5H12. Okay, so the plant engineer has provided the following information, which is the flow rate of the exhaust flow is 1500 CFM. Okay, and this is also continuous. So there are also several assumptions we can make to this problem. So we can assume that the pressure in the exhaust flow is 1 atmosphere, and the liquid density of the pentane is 0.64 grams per centimeter cubed. The operation capacity is 30% of the maximum capacity, right? And it's operating 1 hour for regeneration and cooling. So basically, after 1 hour, after 1 hour of processing the flow, we have to switch, right? We have to switch to another active carbon absorption system to regenerate these saturated active carbon. So the problem wants us to solve for the minimum mass of the active carbon that's needed. So due to the time limit, I'll just basically go through this calculation process. Okay, so if you feel that I'm teaching too fast, you can leave a comment here. I can go back to this explanation. Okay, so let's think about this problem. So you're basically in the process is telling us that we're processing certain gas stream, right? We have its flow rate. Okay, we also know how long it's being operated. This is 1 hour, right? We know what is the concentration of these VOC, right? It's 1880 ppm, right? And also we know what is temperature. Okay, so based on this based on these conditions, let's say this is our active carbon system. We're introducing the flue gas into this packed bag of the active carbon. Okay, so you can relate this system to the system where we talk about the wet scrubber. So the wet scrubber is basically we're introducing some sulfur dioxide and then we're introducing droplets, right? So when we solve for this problem, we listed out what is the target and what is the reality. Okay, so the reality is what is provided by the limestone. And in here, the reality is what can be provided by these active carbon. And the target is just what is the amount of the VOCs we have to deal with in this system, right? So here, I will just separate the problem into 2 parts. We have the target and we have the reality. So the target may be a little bit easier to solve. So I'll just leave the system, leave the blanks like this. Okay. So we know that it's being operated for 1 hour, right? And then we also know what is the flow rate through the system. So we can basically calculate what is total volume of the flue gas over this 1 hour period, right? So that's going to be 60 minutes multiplied by 5500 CFM. And that is going to be, since this is cubic feet per minute, right? So we can directly cancel this unit and further we can convert it into standard units. That is 9344.5 meter cubed. Okay, so this is the total volume for the flue gas. And then we also know what is the concentration of the pentane in this flue gas. That's 1880 ppm, right? So we can calculate what is the volume of the C5, which is the V total multiplied by 1880 ppm. Okay, so that turns out to be 17.57 meter cubed. So basically for the target, we have to deal with this amount of the painting, right? We have to adsorb all of them with the activated carbon. So how much is it in terms of the moles? Because when we solve for the problem, we have to know basically what is the quantity, and the volume here is not correct here. And to calculate what is the number in moles, we need to use ideal gas law, PV equal to nRT. And we know that P is equal to 1 atmosphere, so 1.01 multiplied by 10 to the 5th, 10 to the 5th, and then multiplied by 17.57, which is the volume, equal to N multiplied by 8.314, multiplied by temperature. So the temperature here, that has to be in Kelvin, right? But in this problem, it's providing us the temperature in Fahrenheit. So we have to convert the temperature. Basically, first we can find out that it is actually 35 Celsius. And then the actual temperature is 308.15 Kelvin. Okay, so we can plug in this value and find out that the N, or the total number, or the total moles of the painting that we have to absorb during this 1 hour operation is 692.6 mole. So for our active carbon, we have to deal with this amount of painting. This is our goal. This is our target. Okay. So what is our reality? Our reality is just a bed of the active carbon. Okay. So we have to first look at what is the capacity of the active carbon for the painting, right? It's similar to the wet scrubber, where we have to use the stoichiometry to find out how much sulfur dioxide we can absorb. We can react, right? So it's similar in this active carbon system. We have to find out how much of the painting we can absorb with this active carbon system. So that's why we have to rely on the curve that we just showed. Okay, so we're going to use this curve here. We know that the painting is actually plotted in this curve. But we first need to find out what is the number in the x-axis, okay, before we can calculate what is the capacity. So that's why we need to list this equation here, which is T divided by V prime of log PV divided by P bar. Okay, so so basically we need to plug in the values one by one. And we found that T is already solved in here, which is 308.15 Kelvin, okay? And then in terms of the molar volume of C5, basically it's asking us what is the volume of the painting liquid per mole, right? So first, basically, we can consider just 1 mole of the painting, C5H12, right? We know that 1 mole in terms of the mass, that's going to be 5 multiplied by 12 plus 12 multiplied by 1, which is 72 grams of the painting, right? And further, this problem gives us the density of the painting, which is 0.64 grams per centimeter cubed, right? So we can directly divide 72 by 0.64 grams per centimeter cubed. And then this turns out to be 112.5 centimeter cubed per mole. Let's see, this is not the density. So this is the prime, this is the V prime. Okay, so we got this temperature solved. We got this V prime solved. Now we just need to look at what is the vapor pressure of the painting. So how do we find it? We're going to use this curve here. So if you still can recall for the vapor pressure, when we introduce that, basically when we condense the VOC to collect the VOCs, remove the VOCs, we use this set of curves, right? You can identify where the pentane is, right? And also, since this problem is talking about 95 Fahrenheit, so it's very close to 100, and you can see that basically at this point, the vapor pressure of the pentane is around 16 psi, right? So basically, by using this curve, we can find out that the PV is equal to 16 psi. And then we just need to find out what is a P bar here. So the P bar is the partial pressure of the VOC of the C5H12, right? And then to calculate that, since we already know what is the concentration, which is the 1880 ppm, right? We can directly multiply this fraction, C, by the total pressure, which is 14.8 psi. So basically, it's a definition of the partial pressure, right? So then we can plug in basically 1880 ppm multiplied by 14.7, right? So we're talking about the molar fraction, which is definition of the partial pressure, can relate to the partial pressure, right? And this turns out to be 0.0276 psi. Okay. So based on these calculations, we identify all of the parameters needed for the parameter or for the curve on the x-axis. So if you plug in all of these parameters into this term, you can find out that this is actually 7.569. Okay, so it's around 7.5. All right. Then we can find out what is capacity of the active carbon for the pentane, right? So if you just draw a straight line, 7.5, then refer to here, you can find that it is around 20, okay? So it is around 20, if you further refer to the unit here, it's 20 centimeter cubed of the pentane in liquid per 100 grams of the active carbon. Okay, so we can further write out here that the capacity is equal to 20 centimeter cubed of C5H12 per 100 grams of the active carbon. Okay, so this is the maximum capacity that's established by the isotherms, established by the equilibrium, right? So we mentioned that in industrial application, we cannot reach to this maximum capacity, right? So we normally operate under 30 to 40% of capacity. That's why for this problem, it's assuming that the operation capacity is around 30%, right? So we need to further multiply this capacity by 30%. So let's say the AC5 under the actual operation, okay? Let's say operation is going to be 20 multiplied by 30%, which is basically 6 centimeter cubed of C5H12 of liquid per 100 grams of active carbon. Okay, so this is going to be the actual the actual capacity of the active carbon for absorbing this pentane. Okay, so you see that this unit is actually quite complicated. We can do some simplification, right? Let's just change it to kilograms. Okay, so the EA or the capacity of the C5 for operation is going to be 60 centimeter cubed of the C5H12 liquid per 1 kilogram of the active carbon. We just multiply 10 on both numerator and denominator. Okay, so now we're getting close to the answer. So we know what is the volume of the painting we can adsorb in liquid, right? We just need to convert it into how many moles are there, right? That we can adsorb by the active carbon, right? So first we can convert it into the mass. So that's going to be 60 centimeter cubed multiplied by 0.64 grams per centimeter cubed, right? This is the density of the pentane, right? So that's going to be 38.4 grams of C5H12 per kilogram of the active carbon. Okay, so we know the mass of the pentane we can absorb. Then we can just divide this by the molecular weight of the pentane. 38.4 divided by 72 gram per mole. So that turns out to be 0.533 mole of C5H12 per kilogram of active carbon. So this is our reality. All right. So in reality, for each kilogram of the active carbon, it can only absorb 0.533 moles of the pentane, right? And then we know what is our target, 692.6 moles of the pentane we have to absorb. So then we can calculate what is the active carbon, right? We can just divide this N by the AC5 during operation. 692 divided by 6, 0.6 divided by 0.533. So we're going to have a mass, right? So that turns out to be 1299.4 kilograms of the active carbon. All right, so this is the mass of the active carbon. We're getting very, very close to the answer now, except that we mentioned when we design the active carbon system, we have to design a spiral one, right? So that's why this problem, when it states this question here, it's saying that we also we only operated for 1 hour, and basically after 1 hour of operation, we have to go through the regeneration and cooling. So what this means is that we have to design 2 of this active carbon system. So one will absorb this pentane for 1 hour, right? And then we know that the mass of this bed is this value of, or this weight of the active carbon. Then after this 1 hour, we have to switch the flue gas into this one while letting this first bed to go through the regeneration, right? And because of that, the total active carbon we need is going to be 2 times of the active carbon we designed here. So that turns out to be 2598.8 kilogram of the active carbon. Okay, so this is the final answer. All right, so you can see that this design is quite complicated, but I want you to understand how we're working on this problem. So we also have 2 homework questions about designing the active carbon system. So basically, it's very similar to the sulfur dioxide control. We list what is our target, and then we match our target with the reality to calculate how much of the raw material we need from this process, okay? So I think I probably went through this question too quickly. So I hope after the class, you can read the question again, go through my process again. You can also go through the process in the textbook, okay? So this is the example problem 12.2, all right? So for those who haven't got time to take down all the notes, you can go through the video after the class, okay? So originally I planned to leave around 20 minutes to talk about the project, it seems that we just have 6 minutes now. So I'll quickly go through the questions I received. These are all the questions I got. If you have more, you can, right now you can type it in chat, or you can send it to me offline, or you can even post it on Canvas. Okay, I'll try to answer them. So the first question is, how do we find the size range table of the PM for the cyclone design? So I would say that the best resource you can rely on is a Google Scholar. So I just did a quick search by using the keywords of particle size distribution, fly ash, right, co-combustion, log normal. If you type in these keywords into Google Scholar, there is a list of publications you can find. And I think this one, this publication is what I found, which may be quite useful for your calculation. But I'm pretty sure that there are more publications which you can use. So no matter which size distribution you finally use for your design, you need to list your reference, okay? So I want you to go through this basically literature review process, because in the real industrial design, you have to know what is already known, what is the state of the art, right? We design certain systems. You need to know what people have done, okay? So if you really want to save your efforts for finding the size distribution, you can try to look for the size distribution plotted by provided by the textbook. Also list the reference there. But when you use that size distribution, you need to make sure that it's coming from the co-combustion, right? We don't want it to be some ambient air quality samples that's just measuring the ambient air. So the second question is about how do we account for the lime injection adding to the PM system? So based on the wet scrubbing system, right, you can calculate what is a raw material, raw limestone you feed into the sulfur dioxide scrubber. So for this dry injection, you can also do the same. It's just everything is happening in the gas phase, right? So based on the amount of the sulfur dioxide and hydrogen chloride, you can calculate how much of the carbonate ions it needs, how much of the oxygen, let's say carbon oxide, calcium oxide, or the sodium carbonate, right? So you can use the stoichiometry to calculate the lime that's needed in the mass, right? And then you just need to find out what is the size distribution of the lime. And I think the textbook or the Google Scholar have some descriptions on the size of the dry adsorbents that's injecting into the system, okay? So the third question is, what is the waste product of the lime injection? How does it differ from the lime scrubbing? So the major difference is that the dry injection, we don't generate any liquid waste, right? We just generate particulate matter. So that's why we can use the cyclone system and the ESP or the backhouse to remove the waste that's coming from the lime injection. Okay, so basically, if you inject, let's say, lime into the system, you know that finally you're going to get calcium carbonate, calcium sulfide, right? Or calcium sulfate. Okay, so these species are going to be existing in the form of particulate matter, not in the liquid, because we didn't provide any liquid to the system, right? So you need to find out what is the mass that we introduce to the system. And when you design the PM removal devices, you also need to consider the PM that's generated from this dry injection process, right? So this is a major difference compared to the wet scrubbing system. So how detailed do the technical drying to be, for example, the ductwork? So here I'm basically listing the design from a group that did the work last year. Okay, so I think this is what I'm expecting in terms of your design. Okay, I know that maybe some of you are not very familiar with the AutoCAD. If that's really the case, then you need to consider about making the plot in the PowerPoint. Okay, at least make sure that when we design the duct, they have to be straight lines, right? Instead of hand drawing lines. So this is what I'm expecting you to do, but always you can decide based on your group's effort or group's time. Okay. So finally, what is the expected page requirement for the report? I would expect around 15 pages. So with 15 pages without the references, I think that's quite easy to do because you're doing a lot of calculations for this problem. I think the calculation will already occupy quite many spaces. So I want a report that is succinct, very concise in terms of the description of the system. I don't want you to copy the description on the textbook. So I think 15 pages is quite a realistic goal because last year I saw groups submitting maybe 20 or 30 pages of the report. So let me know if you cannot do this really. So I can maybe try to accommodate this, but what I want to say is that if you feel that you really can't make 15 pages, try to avoid just typing in some, let's say, meaningless descriptions. I want it to be targeted at the project. For example, the calculation, what is a cost, right? So that's what I'm expecting in terms of the report, okay? So this class is the last one before the Thanksgiving break. And after this class, I mean, after we come back, we're going to talk about the meteorology. So basically, this is the last class talking about the air pollutants, okay? So the final exam is going to be comprehensive. It's going to include the PM as well. But I would say more focus will be on the sulfur dioxide control, nitrogen dioxide, and also the adsorber systems. So you guys all have a nice Thanksgiving break, and also try to be careful, okay? So protect yourself and others, all right? Okay, that's all for this class. Let me know if you have questions.
Have a good break.
You too, thank you.